Today we are going to talk about rotation matrix. What is rotation matrix? Rotation matrix is used to relate two frames. The first one is a base frame, X, Y, Z. The second one is rotated, also called the body frame, X prime, Y prime, Z prime. And this frame is rotated about the origin of the base frame. The principle of the rotation matrix is based on projection of axis unit vector pair between two frames. For example, X and X prime as a pair. They are expressed in terms of the vector dotted product, which is equal to the norm of X prime times cosine theta. And theta is the angle between two unit vectors. Since these are the two unit vectors equal to 1, so that's why at the end, the projection just equal to the cosine theta. So sometimes also called the direction cosine. The first case is to transform rotated frame to the base frame. So rotation matrix is called space fixed. Rotation matrix is 3 by 3, indicating the projection of 3 unit vectors, X prime, Y prime, Z prime, onto another 3 unit vectors. So X, Y, and Z. So in rotation matrix, the first column is the projection of X prime onto X, Y, Z. The second column is the projection of the Y prime onto X, Y, Z. Third column is the projection of Z prime onto X, Y, Z. We can also transform base frame back to rotated frame. The rotation matrix in this case is called body fixed. Here, the first column is the projection of X onto X prime, Y prime, and Z prime. And the third column is the projection of Y onto X prime, Y prime, and Z prime. The third column is the projection of Z onto X prime, Y prime, and Z prime. In space-fixed rotation matrix, X, Y, Z are in column vector, while in body-fixed rotation matrix, X, Y, Z are in row vector. So that's why the body-fixed rotation matrix can be expressed as the transpose of the space-fixed rotation matrix. There are 3 rotation matrices. The first one is the rotation about the x-axis. Here is the base frame, X, Y, Z. X is a unit vector, 1, 0, 0. Y unit vector 0, 1, 0, Z unit vector 0, 0, 1. This is a rotated frame about the x-axis by angle theta x. The space-fixed rotation matrix is given below. The first column is the projection of X prime. X prime is in line with the X, so it's a 1, 0, 0. Second column is the projection of Y prime. Here is the Y prime. Projection around the x-axis. There's no projection, so it's 0. Projection around Y is cosine, and projection around Z is sine. The third column is the projection of Z prime. So Z prime is here. So there's no projection around X, so it's a 0. And projection on Y is in the negative direction. So this is the one. And that's a sine, so that's why you see the negative sign. Projection on Z is cosine. So in this case, the sine and cosine actually on the bottom right corner. The body fixed rotation matrix can be obtained by doing the transpose of the space fixed rotation matrix. As you can see, the sign is flipped. And we can also check whether it's true or not by using the projection method. So in this case, the first column is the projection of x-axis. So here's the x-axis, which is in line with x prime. So that's why it's 1, 0, 0. The second one is the projection of y. Here's the y. So projection on the x prime is 0. The projection on y prime is a cosine, and the projection on z prime is a sine, but it's in the negative direction, so it's a minus. The last column is the projection of z. So here's z. So obviously there's no projection on x prime, so that's why it's 0. So there's a projection on y here, this y, but it's the opposite direction. Also y prime, sorry, so on 1 prime. So that's the projection. So it's the sine theta, and the projection on the z prime here. So there's a cosine. This is the second rotation matrix about the y-axis. Here is the base frame, x, y, and z. This is rotated frame about the y-axis by angle theta y. The space-fixed rotation matrix is given below. So here, the first column is the projection of the x prime. The x primes are here. The projection on x is here. That's cosine. There's no projection on y, so that's why it's 0. And the projection on z is this way, here. But it's in the negative direction of z, and that's equal to sine theta. So it's a sine, but it's a minus. The second column is a y prime. So y prime is in line with y. So that's why it's 0, 1, 0. The third column is the z prime. So here's z prime. So you have the projection on x, which is this one here. That's a sine theta. And then there's no projection on the y, so that's why it's a 0. And you have a projection on z, that's a cosine, which is this one. And in this case, sine, cosine, they are on the 4 corners of the rotation matrix. For body fixed rotation matrix, you can obtain that by doing the transpose of the space fixed rotation matrix. Again, like the first one, we can check by using projection method. The first column in this case is a projection of x axis. So the x-axis is here. So the projection on x prime is a cosine here, and the projection on y is none, so it's 0. And the projection on the z prime, which is this one here, is sine. This is a positive. The second column is the y projection. So y is in line with y prime, so that's why you're getting 0, 1, 0. The third column is the projection of z. So you have z here. The projection on x prime, so there's x prime, is sine, but it's in the negative direction. So that's why you get the minus. But you don't have the projection on y, so you're getting 0. Around the z prime here, the projection of z onto z prime will be cosine. So that's why you'll be getting this one here. The third rotation matrix is about the z-axis. Here is the base frame, x, y, and z. This is rotated frame about the z-axis by angle theta z. The space fixed rotation matrix is given below. As before, the first column is the projection of x prime. Here's x prime. The projection on the x-axis is cosine. The projection on the y-axis is sine. So there's no projection around z, so it's 0. The second column is the projection of y prime. So y prime is here. The projection on the x-axis, which is equal to here, but in the opposite direction. So it's a sine with a minus. The projection on y is here. That's equal to cosine. And there's no projection around z, so it's a 0. The third column is a projection of z prime, because z prime is in line with z, so that's why you're getting 0, 0, 1. In this case, cosine sine on the upper left corner. For the the body fixed rotation matrix, you can obtain that by doing the transpose of the spacer fixed rotation matrix. You can see just a swap, right? Just a swapped here. But as before, we can check by projection method. So in this case, the first column is a projection for x. So here's the x. So you have projection on x prime, which is cosine. This one here, and you can have the projection on y prime, which is this guy here, the sine, but it's in the negative direction here. So you have a minus. Obviously, you don't have any projection around z, so it's a 0. The second column is a projection for y. So here's the y. For the projection on x prime, you have this one here. That is the sine, so you have sine here. For the projection of on the y prime, this one here, and you have a cosine. You have a cosine here, so that's why you have a cosine. So obviously, this one doesn't have the projection on the z, so it's a 0. The last one is the projection of z. So this one is z, right? This one z. So z is in line with the z prime, so that's why you're getting 0, 0, 1. Okay, with that, we can perform some general rotations. Example, and there's a frame XYZ attached to this box, and the box is rotated around Y by 90 degrees. This is the rotated orientation. So Y prime is the same because that's the rotation axis. The X prime is horizontal from vertical. The Z prime is vertical from horizontal after rotation. And then we further rotate this box about the Z prime by 180 degrees. So this is the final orientation. The Z double prime will be the same as Z prime. The X double prime will be opposite direction of X prime. And the Y double prime will be the opposite direction of the Y prime after rotation. So now we want to write the rotation matrix, okay, from this frame relative to the base frame. So we can use the projection method to write that. Here's the rotation matrix, we can check. The first one is the X double prime, and we see the X double prime is in line with Z, so you're getting 0, 0, 1. The second one we check is the Y double prime. Y double prime is in line with Y, but in the opposite direction, so you're getting 0, minus 1, 0. The last one we check is the Z double prime. Z double prime is in line with the X, so you're getting 1, 0, 0. And you also can also get the results by using the rotation matrix that I mentioned to you before. So first one is rotation on Y, which is this one here, by 90 degrees. And the second one is rotation about Z by 180 degrees. As you can recall, for the rotation matrix on Y, sine, cosine on four corner elements. So diagonals are always a cosine. Okay, so you have cosine, cosine here, cosine 90 degree will be 0. Off diagonal is sine. So you have sine 90 degree is 1, minus sine 90 degree is minus 1. The second one is the rotation matrix on Z. As you can recall, the rotation matrix about Z, the sine, cosine are on the top left corner. So diagonals are always a cosine. Then the cosine 90 degree, the cosine 180 degree will give you minus. The off diagonal is sine. Sine 180 degree will give you 0. And then now we can do the matrix multiplication. The first row to the first column is 0 here. The first row to second column is also 0. The first row to third column, you have a 1 times 1, so you give you 1 here. So we can continue with the second row. So second row to first column is 0. The second row to second column, you have a 1 times minus 1, so you're getting minus 1. So second row to third column, you're getting 0. The last one is the third row. The third row to the first column, minus 1 times minus 1 give you 1. And third row to second column, it will be 0. And the third row to the third column will give you 0. So we are getting the same results. So I hope that the projection method I introduced to you for getting the rotation matrix is a very effective one. Thank you very much for your listening.